screen now?
Yeah.
Okay, no worries, Paris. No worries. Okay, guys. Just before we start, have you finalized the groups for assessment 1? I can see some of you have already joined groups, but some not. Can you please finalize everything for the group members? Do you have any question from last week tutorial, or do you have any question generally about the course?
So,
Yeah, Ahmed, I got a few questions just relating to the assignment, but I can leave that till the end if you like.
Okay, no worries.
Yeah.
And have you all joined the groups? Because I received some emails that you need me to add you to the groups, but actually it is better to join the group yourself so that you can have communication with others. So all of you have joined groups, or the attendance today have joined groups?
Yep.
Okay, that's good. Thank you, Elias. Okay, so I think we can start our tutorial today, or our workshop today. So have you looked at the course content of week 3 before the lecture or not yet? Have you had time to look into the materials?
Yeah. Not really.
Not really? Okay. Okay, anyway, so today we will be talking about the wind actions in Australia. As you know, the wind actions in Australia are covered by, I just switch off my video. The wind action in Australia are covered by the Australian Standard 1170.2, and the new version, or the latest version of the Australian Standard, is 2021. And today our topics will be regarding the calculation of wind action, like wind speeds and wind forces or wind loads on the structures. So to calculate the wind speed and wind loads, we need to calculate some parameters and some factors. So we need to find the regional wind speeds, site exposure multipliers, aerodynamic shape factor, C shape, and the dynamic response factor, C dynamic. Okay, so mainly all our lecture today will be about wind loads and all the data extracted from the Australian Standard 1170.2. Okay, so you can have a look on the Australian Standard, and also this is the reference book. You can have a look on how to calculate the wind loads in this book. Okay, so the first step is calculation of wind load. So we have the pressure extracted by the wind on any part of the structure depending on the shape of the structure and the direction of the wind. We have some definition. We have windward and upwind slopes, obviously beach roofs. This arise in pressure above atmospheric pressure. So the pressure in these cases will be above the atmospheric pressure. What is the definition of windward wall? So if we have a building like that, so if the wind coming in this direction, so the wall facing the wind is called windward, okay? And the opposite one at the back is called leeward wall. So we have windward wall and leeward wall, and the sides, the blue ones, are called side walls, So this all for this wind direction. So if we have this wind direction, so we have 4 walls. The wall facing the wind is called windward. The opposite on the other direction is called leeward wall. The 2 walls on the sides are called side walls. Okay. So we have side walls, leeward walls, and leeward slopes of roof and flat roofs. We will have section on the outside. So based on this, what is this meaning? So what is the meaning of this? So if we have this building again and the wind coming in this direction, so the windward face will be under pressure, but the other 3 walls, the leeward walls will be under suction, and also the side walls will be under suction. So we have some walls under suction, some walls under pressure. Pressure means the force, like acting onto the wall. Suction means the forces or the pressures come out of the wall. Okay. The greatest suction pressure near edges of roof and the wall. So the areas near the edge has like higher pressure or higher intensive pressure compared to the general areas. The internal pressure means pressure inside the building. So if you look at this example here, so this face, for example, is our roof, and these 2 are the walls. So from outside, as you can see here, if the wind coming from this direction, wind direction. So this, what is this wall name, or what is the type of this wall? Windward. This windward will be under pressure. And the pressure in our case, take the sign, the positive sign. So the positive sign is for the pressure. So the other side or the other wall is called leeward wall, and it will be under suction. Okay, so this for the walls. For the roof, we have also 2 types or 2 definition. This face opposite to the wind is called upwind slope. So upwind is for the roof, and the other slope here is called downwind slope. So the upwind, as you can see, is under pressure. And the downwind is under suction. Okay, so this all for external pressures. So all this is external pressure. What about the internal pressure? The internal pressure means the pressure from inside. So this blue or sky blue is internal pressure. So the internal pressure depend on here, this definition here. We have positive values or pressure pushing the walls or roof, dominant opening on the windward side only. So if we have opening, like somewhere here, there was some opening here. So if we have opening on the windward, so we will have this type of loads or pressures. We will have positive pressure pushing the wall and roof outward. Okay, the other type or the other option is negative, sucking inwards. Openings are on the side walls or leeward wall. So this is just a brief or some examples about the wind. So depend on the case of the opening. So here the opening was in the side, the windward wall. Here the opening is in the side walls. We will see this in details later. Extreme storm wind gusts usually cause damage considered by Australian standard. So the extreme storm also considered in the Australian standard. Uneconomic to design the structure to remain totally undamaged even on extreme storm, because the extreme storm is rarely happen. So you cannot design only for this rarely situation. So in some cases, we may allow for damage or some damage based on the severity of the extreme wind or the extreme storm. It is normal to use two wind speed in design. So we have two wind speed for design. Ultimate, if you remember from last week, we have two limit states. We have ultimate limit state, ULT, and serviceability limit state, SLS. So the ultimate wind speeds unlikely to occur during the structure life, but could occur at any time. So this also some extreme case, but we design for that. Some minor damage is acceptable in this case, but the structure must not totally collapse. So this design method allow for small damage in the elements. Serviceability limit stage, which will be used if we are checking for deflection and vibration and so on, if you remember last week. So we have designed for a lower wind speed is used in this design method. The structure should survive without any damage in this case. So the serviceability limit or the speed for serviceability is less than the wind speed for ultimate. So this should be in mind that the wind speed for serviceability is less than ultimate wind speed. This is also important note we should know or we should keep in mind that all the calculation related to the wind design are in accordance with this standard, and all the calculation in the standard are for ultimate calculation. So all the calculation, or sorry, all the calculation and formulas given in the standard for ultimate. So we need to use like conversion or a factor to convert to serviceability. So if you want to check for or design for serviceability, you need to convert the values you got from the Australian standard using a factor. We will talk about this factor later. Let's start now with how to calculate the speeds. So first of all, our first step is to determine the site wind speed, V site beta. So what is the reason for V site beta? Just if we go scroll down a little bit here. So this is our main formula we need to use, which is the design wind pressure B. So the design wind pressure B is equal to 0.5 rho air. Rho air is the density of air. V design theta is called design wind speed. And then we have two factors, C shape and C dynamic. Okay, so in this case, if we look at this formula, this is the important formula we need to know. Density of air is known, and it is a constant value of 1.2 kilogram per cubic meter. Okay. So to calculate the design wind pressure B, what should be known first? The design wind speed. The design wind speed is using the site wind speed. So the site wind speed is important to find the design wind speed. and then the design wind speed will be used to find the wind pressure B. Okay, so if we return back to our formula now, the site wind speed is the wind speed at the site of construction, and V site has 8 cardinal direction. Beta is the reference height. Sorry, beta is the directions. So we have 8 direction. Each direction has theta, or sorry, angle of beta. So we have beta 0, beta 45, and beta 90, and so on. We will see that. At the reference height Z or Z above the ground, calculated as follows. So this is our formula for site wind speeds. So how many site wind speed we have, if you know? How many site wind speed? 8 site wind speeds. So the 8 site wind speed for beta equal to 0, beta equal to 45, beta equal to 90, beta equal to 135, and 180, 235. Okay, just make sure, sorry, 225. Okay, and then 270, and then 350. Okay, so these angles are here as well. So this is the beta values. Okay, so we have this 8 values of beta. Okay, so this is the 8 directional or 8 cardinal directions for site wind speed. Okay, so how to find V side beta? V side beta is equal to VR times MC times MD times MZ category times MS times MT. So we have VR is called regional gusset wind speed. And we have this 5 multipliers. So the site wind speed, V side beta equal to the regional gusset wind speed times this 5 multipliers. We will talk about them now. So we have VR is the regional gusset wind speed in meter per second for average recurrence interval of R years. So we have R, or 1 per R, as given in section 3 of the standard. So we have MC, which is called, or it is the climate change multiplier. So we have MD is the wind directional multiplier for the 8 directional or cardinal directions. So MD is the factor that give us 8 values of V side theta, V side beta. And then MZ category is the terrain height multiplier. MS is the shielding multiplier. MT is the topographic multiplier. So these are generally what we need to calculate to find the site wind speed, which will guide us to find the design wind speed. Do you have any question, guys, up to now?
Just one quick question. With what happens when the building's offset a little bit in the angle? How does that work with your angles?
Yeah, we will talk about this now. So depend
okay.
on the building orientation.
Yeah.
But it's just generally the formula and how to define the parameters. Okay.
Yep.
Okay. So here, generally, the speed is determined, the wind speed is determined as the average roof height of the building. In some cases, this varies according to the structure. So the standard also give us how to find because the height is essential in the calculation of the building. So for example, if we have like a beach roof, so this is H. So H is the middle height of the beach roof. And here how to find H if it is on a slope or something. And here H of this type of like tower or something. So this is H up to the highest point. And if the building is regular, so this is H. Okay, so this also video shows the wind direction and the wind speed. So you can have a look on this one. So let's talk about now the 8 direction of side beta, or sorry, the cardinal direction of the building, and how to use the cardinal direction or the side wind speed to find the design wind speed. So just need to add a page here. So if we look at the directions here, so for example, if we have a building with an inclination like that, so this is the cardinal directions. This is, I will start with this. This is the axis of the building. So the cardinal direction we have are the blue ones here. To have beta equal to 0. So this is north, east, west, and south. This is the main direction. And in between we have at 40 degree, we have northeast direction. And here also we have southeast direction. And we have southwest direction, and we have northwest direction. So here beta 0, beta equal to 45, beta equal to 90, beta equal to 135, beta equal to 180, beta equal to 225, beta equal to 270, sorry. And here beta equal to 350. So this is the blue ones are what they are called cardinal direction. So based on the formula we mentioned earlier, we can find V right beta equal to VR times M D MC times MD times MZ category times MS times MT. Okay, so for each direction, we will find the cardinal or V site beta. Okay, so for our building, if the building, the axis of the building is the green axis, not the original axis. So we have 4 other direction of the building. So for the site, we have 8 cardinal direction, and with a different color here. For the building, we have 4 direction only. These 4 directions are the design, wind speed direction. So we have, for the building, we have normal, and we have east, we have south, and we have
Excellent.
west. Sorry, do you have a question? Okay. So if you look here, so as you can see here, this called orthogonal building orthogonal axis. So if we update our building, so the green ones are called building orthogonals or building orthogonal axis. The building orthogonal axis at theta equal to 0 for the east, theta equal to 90 for the south, theta equal to 180 here, and finally theta equal to 360 for the north. Okay, so now how we find, after we find the site wind speed, the cardinal wind speed, how many we have again? 8. So we need to convert the 8 cardinal wind speed to 4 orthogonal wind speed. So the idea is each wind speed for the orthogonal lie between 2 axes. So the wind speed at the north, we write down here. I need to. So V design and theta equal to 360, which is for the north direction. What do you think? Which V side theta to take? Which V side beta to take? Northeast or north? The north is lying between these two, right? So the design wind speed will be the largest or the biggest of V side beta 0 and V side beta 45, or for the north direction and northeast direction. So we will take the maximum of these two. So each orthogonal direction will lie between 2 cardinal direction, and the design wind speed will be the maximum of these two. So if we apply this here for the east direction, what is V design 0?
$135.
Yeah, it is the largest between these two, right? So all the time it will be lying between 2. It is this direction, the east direction, the orthogonal east, lie between 2 cardinal direction, east and southeast. So V design will be the largest of these two, so beta 90 and beta 35. Okay, here for the orthogonal south, V design 90 equal to the maximum of these two, beta of 180 and beta 235. Okay, do you understand it?
Yeah, that's good. Thank you.
No worries. So what is the last one, William, if you can help me with this one? So the last one is the orthogonal west. So V design 180, how much? The maximum or the largest of?
The value of west or
Yeah.
northwest.
Yeah, west or northwest. That's right. So beta 270 and beta equal to 350. 15. Okay. So do you understand it? So the main thing is to determine V side beta. So if we got V side beta correctly, so we can easily find V design. So again here, we need to find V side beta. We will have 8 values. The 8 values will give us 4 orthogonal design wind speed for the building. Okay. If the building or the axis align with if the orthogonal align with the cardinal direction, is this a problem or this will be easier for us? This will be easier. So for example, if we have a building like that, so these are the cardinal wind speeds. And the orthogonal wind speed will align with them. So if you get the cardinal wind speed, you can easily find the orthogonal wind speed. Okay, so this will be only a special case, not all the time like that. Okay. So for example, if the blue one is the orthogonal, so the orthogonal we have theta equal to 360 and beta equal to 0. So this means that V design and theta equal to 360 equal to V site beta equal to 0 because it is already aligned with it. Okay, so this is generally the idea of calculating the design wind speed. So here's the design wind speed V design theta. You can read this, but there is 2 methods. We don't need this method here. So are you okay with this method? They are both similar, but just with the drawing and with this curve. So we can extract the orthogonal wind speeds from the cardinal wind speed. Do you have any question, guys, for the how to get the design wind speed from the orthogonal wind from the cardinal wind speed or the site wind speed?
No.
Okay, thank you. Now, if we jump to the design pressure and distributed forces. So again, here is after we got the design wind speed, again, this is our requirement or our what we need to design our steel structures. So we need to find the wind pressure. So again, the wind pressure B in pascals equal to 0.5 rho air, the density of air. So rho air, the density of air can be taken as 1.2 kilogram per cubic meter times V design theta squared. V design theta is the building orthogonal design wind speed at theta 0, 90, and 180 and 275. And then C shape and C dynamic. Again, C shape is the aerodynamic shape factor. It's just Hello guys. Can you hear me now?
Yes.
Yeah, that's good. I'm just waiting for some of you to connect. Okay, guys, thank you for waiting for me. So again, we have the factor we need to calculate is C shape. Not having again. C shape and C dynamic. C shape is the aerodynamic shape factor in section 5, and C dynamic is the dynamic response factor in section 6. This value can be taken as 1, except for the structures that is dynamically wind sensitive, or like this means that if the building are subjected to dynamic loads, you can find the value for C dynamic. Otherwise, it can be taken as 1. Okay, so some of the parameter can be taken as 1 for simplicity, but if it is sensitive or need to be calculated, you can refer to the standard to find. Okay, so the wind actions, we have the wind action again. We have surfaceability wind action and ultimate wind action. So the wind actions shall be determined given these two clauses, and I think this part is not important for us, so you can ignore this one. Okay, so because this is just multiplying to find the force, you need to multiply the pressure we got already times the area. So this is logically made, so we don't need this one here in our course. We can just read it quickly. So now, if we go to find the parameters in details, if you remember, again, we have V site beta equal to VR times some multipliers, MC, MD, MZ category, and MSMT. So this all the parameter we need. So the first value or the first parameter we need to calculate or need to determine is the regional wind speed, VR. So VR is the regional wind speed, and according to the Australian standard, the map of Australia is divided into 5 regions. We have region A, B1, B2, C, and D. And region A is subdivided to A0 to A5. So based on the location of the city or the location of the building you are designing, you can refer to this map and find where is the location. For example, if we are in like, for example, Brisbane here, if you look at Brisbane. So Brisbane is region B1. For example, here Perth A1. So depending on the location of the building, you can decide which region is your building, and you can see most of the area or the inside area of Australia is A0. And here is a table, give us the regional wind speed based on what? So the regional wind speed will be based on 2 factors or 2 parameters we need to know. Firstly is the region. So based on the location, you decide what is the region, and then you need to find which one to assume or to get. So we have V1 up to V1 10,000. This is called 1 to R, which is the recurrence interval. So the recurrence interval R can be found from this, or need to be found to use this table. So if we get 1 to R, so for example, if 1 to R is 1 to 200, so you get V200. Then, for example, if you are region B1, for example, so what is your regional wind speed? Regional wind speed will be 52. So we need two things or two data, two information to find the regional wind speed, the region, and the recurrence interval 1 to R. So how to find the recurrence interval R? The recurrence intervals R is the average time interval between the exceedance of the listed wind speed. So this is how often is the extreme winds happen based on the statistical analysis of the wind. So for ultimate and limit wind speed, this can be used. For R more than 5 years, it is equal to the reciprocal of the annual probability exceedance of the wind speed. So we can consider the average recurrent interval is the annual probability of exceedance. Okay, and this is the Australian or the wind region given by the Australian standard. Okay, but how to find what 1 to R? So this is important. So how to find 1 to R or the interval value? Let's try to find it here. Okay. So 1 to R will be found from using the Australian standard 1170.0. So the 1170.0 will give us the probability exceedance, annual probability of exceedance, or the recurrence interval value R we are looking at. So using the Australian standard 1170.0, depending on the importance of building. Okay, so I will just share with you now the file, the 1170.0. Have you downloaded the standard or not yet?
Yeah, I couldn't download it. I could download.
I have sent you
online.
I think 2 of them. Do you still, but you cannot download the Wind one. I have sent you the steel standard and I think 1170.1 or 10, I can't remember.
Oh yeah, if you sent us whatever you sent was I downloaded that.
Okay.
Did you send both of them or just the one?
I sent 2, but I think I didn't send the standard for wind, the 1170.2.
Yeah, I
Maybe
think that-
I have to add them to the, I will check with Mustafa if it is allowed to share them on the website or maybe like copyright or something. So if not,
Okay.
I will send it to you by email. Okay.
Yep.
Okay. So I will just share the other file with you. Can you see the standard?
Yep.
Yeah. So this is the 1170.0. Okay, the general principles of the loading in the Australian standard. So if we go to section F, appendix F, this is the annual probability of exceedance, which equal to our R. So this depending on, we need to find the, as I told you, we need to find the importance of the building. So we have few importance level of the buildings to design. So we have low, take the importance level 1 from 1 to 5. So low for the building that low consequence for loss of human life or small or moderate economic or social environment consequence. In this like minor structures, failure not likely to endanger human life. So for simple or small building that will not threaten lives of people. Ordinary, the importance level 2, which is most of the building we are designing. So medium consequence for loss of human. This like in normal structures and structure not falling into other levels. Those for our maybe our course we usually will at level 2. High consequence of failure, so high consequence of loss of human, very great economical or social or environmental consequence. So we have two levels, 3 and 4. 3 for major structures that affecting crowds, like for example, schools, universities, and so on. And number 4 is post-disaster structure that need to be function after the disaster. For example, after earthquakes, the hospital need to be working to like give treatment to people and the police station and so on. So this type of building will be level 4. The exceptional circumstances where reliability must be set on a case-by-case basis. This important level 5, which is exceptional structure, like for example, nuclear structure and so on. So mainly our building will be between 2 and 3. Like for example, if we are designing a warehouse for shopping center or library or so on, so you need to take it as 3. For normal building can be taken as 2. So these are the importance level. So if we get here to table F2, table F2 will give us the annual probability of exceedance based on the importance level. Okay, so if we look here, how to use this table. So what we are designing for wind. So we are looking on this column. So here is the importance level. We need another information to get into this table. The other information is the design working life for the building. So for example, if the building is like governmental building or house or so or bridge or something, so we can take the design life of the building as 50 years. So we need two values or two information, the design life and the importance level. For example, if we have a design life of 50 years and a building of importance level 2, so how much is the interval or annual probability of exceedance? 1 to 500. So for this case, 50 years and importance level 2. So 1 to R is equal to 1 to 500. So which VR we need to get? V500. Okay. Do you understand this one?
Yep. Thanks.
Yep.
Yeah, okay. So V is depending on two parameters, the importance level and the design life. So 50 years, for example, with importance level 2, the occurrence level is 1 to 500. So if we return back to here, our table, so for example, if we have V500 here with a region of B1, for example, so how much VR? VR equal to 57 meter per second. Okay, so this is how to find the original wind speed. So the original wind speed depends on the importance factor or the importance level and design life. Okay, so after we got the VR or the original wind speed, the next parameter or the first multiplier we have is the wind direction multiplier. The wind direction multiplier can be taken as 1 for structure as chimneys and so on, for cladding, which might be not our cases. So if this one of these cases, so you can take it as 1. Otherwise, the wind direction MD for all region can be taken from table 3.2a from the Australian standard as follows. So as you can see, how many cardinal wind speed we have, wind direction we have? 8 cardinal direction. So for each cardinal direction, we will have a value of MD. So what is the information needed to use this table or to find the parameters, if you know? So we need to know the wind region. So for example, if we have wind region B1 or A1 or so on. So for example, B1 from the previous example here. So how many factor we are using? 8. Okay, so we will have 8 MDs. So we get this 8 values of MDs. So that's why we have 8 cardinal wind directions, because we have 8 values of MD. Okay. So at the end I will show you after we get the factor how to like arrange the data we got. So the next multiplier is MC. What is MC? MC is the climate change multiplier, can be taken as follows. So MC as well is depending on the wind region. So based on the wind region, for example, so how much MC? MC equal to 1. This is just an example. The next multipliers are the site exposure multipliers, which are MZ category times MS times MT. So the category, the terrain category, times the shielding multiplier times the topographic multiplier. So these three, the site exposure multiplier, are parameter related to the site condition. So this parameter depending on the site condition around the building. We have terrain height multiplier MZ category, shielding multiplier MS, topography multiplier MT. Let's start with MZ category, the terrain multiplier. So the terrain multiplier, sorry, the MZ category or terrain height multiplier depend on the terrain category level. So how many terrain category level? We have TC1, TC2, and so on up to TC4. So we need to define the terrain category multiplier. The terrain category multiplier depends on terrain over which the approach wind flows towards a structure based on the following categories. So you can define the area surrounding the building into this 5 category. For the first one is terrain category TC1. This is very exposed open terrain with very few or no obstructions and all water surface. So in this case, we don't have many or any obstruction, almost any obstruction. So it is open area. And for the open area or the exposed area, the wind will be more intensive and will cause more abrasions. Terrain category 2, it is open terrain, but including grassland, well scattered obstruction, having height generally from 1.5 to 5 meter, with no more than 2 obstructions per hectare. So for example, in this case, we have maybe 1 or 2 categories in per hectare. Each one of them, the height is only 1.5 to 5 meters. So it has very small obstruction and maximum 2 per hectare. Terrain category 2.5 or TC 2.5 is terrain with some trees and or isolated obstruction, outer urban areas. So the outer urban areas can be considered as TC 2.5 with few scattered house with more than 2 and less than 10 building per hectare. So here, the other 2.5 will be between 2 and 10 houses or obstructions per hectare. 2 is only 2 obstructions. Terrain category 2.5 is from 2 to 10. Terrain category 3 is same terrain with numerous closely spaced but more obstructions, having height generally from 3 to 10 meter, equivalent to more than 10 houses, at least 10 houses or 10 obstructions per hectare. So the third one is more than 10 houses per hectare. This is TC3, this is TC 2.5, this is TC2. Okay, terrain category 4 is inside the large cities and well-developed industrial complexes. So terrain with numerous large heights, 10 to 30 millimeter tall, and closely spaced construction, such as large city and well-developed complex. So based on the situation of the building or the design, you can define or can assume how much our TC. Okay, so after we know TC, the terrain category classification, so we need to determine MZCAT. The variation with height Z of the effective terrain roughness on wind, terrain and structure multiplier ZCAT is taken from the following table. So this table is for all gusset wind speed in all terrains except for A0. So for A0, it has a different variation. You can look at the note under the table here. So based on the building height Z, so for example 15 meter, and based on your terrain category, so for example we have terrain category of 2.5 TC 2.5, so how much MZ category? 0.97. Okay, so also for the design we might have more than one terrain category. Like for example, if you have this our building, so you have orthogonal north, orthogonal east, orthogonal south, and orthogonal west. So you might have MZ category for north direction, different from Z category for east direction, and so on. So depending on the wind direction, you can define how much is the MZ category. Okay, like for example, if this area has like only 2 obstructions, so this can be defined as TC equal to 2. For example, if from the south we have like 10 obstruction, so this can be defined as TC 2.5 or 3, right? So the terrain category can be different in different directions, so that's why you can have different MZ category for different directions. Okay, the next multiplier is the shielding multiplier. The shielding multiplier MS is shielding is provided by upwind building or other structures. Shielding cannot be provided by tree or vegetation. What does this means? This means that, for example, if you are designing this building, and if you have another building in front of this building, so when the wind blowing in this direction, the building in the way of the wind will cause shielding on the designed building. Okay, this shielding will cause reduction or less wind speed or less wind pressure, right? Is that logic? So the shielding might reduce the wind pressure on our design building. Upwind building cannot be used to provide shielding on a slope with a gradient greater than 0.2 unless it is over its overall height above common datum such as sea level exceeds the height of the subject building. So this means that if we have a building, a shorter building, so this shorter building, if the wind coming from here, cannot be used as a shelter because it is shorter or smaller than our building. Okay. And here is an example. If we are designing this building, so if the wind coming from here, this can be considered a shielding building as the elevation exceeds the building being shielded, but this one cannot be considered because it is average slope more than 2 and the elevation is less than the building being shielded. Okay, and also similarly this one. Another parameter, another factor is if the building is at distance more than 20 times the height, so cannot be considered as a shielding building. Okay. So the shielding multiplier MS can also be taken as 1 for structure with H greater than 25 meter, where the shielding effect can be ignored. You can take MS as 1 if the building height is more than 25 meter and the shielding effect can be ignored. The shielding multiplier that is appropriate to a particular direction is taken as in the table. So again, the shielding, depending on what direction you are designing. So for example, we have here east, west, south. So the shielding from this direction different, from this direction different. So each direction can have a different MS. So you can have MS west, MS north, MS south, MS east. Okay, they can all be same also, but the general case or the actual case should be different because you cannot find the shielding from all directions same. So how to find the shielding parameter or shielding multiplier MS for building with H less than 25? So if you look here, we need to find something called the shielding multiplier. So to find the shielding multiplier, you need to find the shielding parameter S. So to find MS, you need to find S. How to find S? So building providing shielding, only building with a 45-degree sector with radius of 20 times the height, with height greater than or equal to H are used to provide shielding. So this means that we look here. So if we have a building, so Again, we have direction. So for example, if you are studying the south direction, so we need to study only the building in a sector of 45 degree. Sorry. So a sector of 45 degree and within a distance of 20 times the height of the building. So if the building height is like, for example, 10 meter, so you need to only study within 200 meter sector. So for example, if this is our sector, so we will only study the building in this sector. So if we have, for example, these 3 buildings, so we are studying the wind in the south direction like that. So these are 3 buildings to study. Why we study this 3 building? Because these 3 buildings are lying in this sector here, which is the 45 degree sector. And the other condition is 20 times the height. Another condition is the building height. Like for example, H1, H2, H3 should be more than 10. The building's height should be more than the design building. So if our building height is 10 meter, so if the building height is more than 10 meter, we can consider. Otherwise, we have to neglect. Like for example, if we have building here with h equal to 5 meter, so this cannot be considered as shelter. So now we know how to or which building to study. Now how we find the parameter S. So for the parameter S is equal to this formula from the standard, LS over root HS PS. What is LS? LS is the average spacing of shielding building equal to this formula H times 10 over NS plus 5. Where HS average roof of the shielding buildings, BS average breadth of the shielding buildings normal to the wind stream, H is the average roof height above ground of the structure being shielded, NS number of upwind shielding building within the 45 degree sector of 20 times height, with HS more than H. So if we look back here, so the first step is to find LS. How much LS? H times 10 over NS plus 5. So what is H? Can you help me with this one? H is our building height, for example, 10 meter. N is how much? N is how many buildings we have? 3. So N is equal to 3. So now you can find LS. The next step after you find LS is to find S. S equal to LS root HS BS. Okay. So if we have more than one building, so this will be summation. Okay. Is that okay? Yeah. Okay. So for example, if we have we have BS1 equal to like 20 meter and this BS2 15 meter, this 3 and 18 meter, for example. So you can find this. So LS is this formula above, and the root, we have the height of each building, HS, times the width of each building, BS. So now you can find S. So after we got the value of S here, for example, if S 3, so you can get the shielding multiplier as 0.8. What if any parameter lie between two values, like for example 4.5? So how can we find that? You can use interpolation, linear interpolation. So if it is like, for example, 4.5, so you can take the middle point, 0.85, for example. Okay. Do you know interpolation? Do you know how to do interpolation?
Yeah, but it's not fun.
Yeah. It's not, it takes time, but for example, if it is close to one value, you can take this value. Like if it's close to the middle, like for example, the middle one will for example, if it is s equal to 4.5, so you can take it the average or the half, like 0.8 plus 0.9 over 2, so it will be 0.85. So for example, if it is 3.5, you can take it as 3. Okay, so for our calculation, you can, just to save time and because it will not affect much, so you can take the closest value to it. But if you want the exact value, so you need to do linear interpolation, okay, with any parameter. Do you have any question, guys, up to here?
No.
No, all good, thanks.
Okay, so the next parameter is topographic multiplier MT. So the topographic multiplier MT is taken in accordance to the following cases. So we have some cases for sites in region A4. Okay, and for sites for region A0 and elsewhere, the larger value of the following. So if we are in A4, so you need to find this value, MAT equal to MH MLE multiplied by 1 plus 0.3015E, where MH is the Hell shape multiplier, MLE is the Lee effect multiplier, can be taken as 1. E is the site elevation above mean sea level in meters. For sites with in region A0, MT equal to 0.5 plus 0.5 MH. Elsewhere, any other region, so MT is the largest of these two values, which are MH and MLE. So we need to find MH and MLE. MH is the Hill shape multiplier. The Hill shape multiplier is taken as 1 outside of the local topographic zones in figures 4.3 to 4.5 from the Australian standard for h less than 10 meters. So if we look at this shape here, so this is the shapes or the figures showing the MH multiplier and how to use it. So if we have hills and ridge case, escarpment case, and hill and escarpments having upwind slopes greater than 0.45. So here we might have this local topographic zone. So if the building is in this area, so this case, if it is outside this area, so it is a different case. So this is what is mean by the local topographic zone. So if the hill shape is if the building is outside of the local topographic zone, you can take MH as 1. So for this case, MH can be taken as 1. Okay. What is this local zone definition? So if we have a hill type, the height of the crest is h. So LU is the distance from half of the height to the crest. So this is LU, and we have L2 equal to 1.44 LU or 1.6 H in both sides. Okay, so if the building on this local topographic zone defined as by LU and L2, so you can use, or you have to find the value of MT using these two formulas. Okay, so within the local topographic zone, the hill shape multiplier MH is assessed for each cardinal direction. So we have 8 values, considering the most adverse topographic cross-sectional. So you can take the critical of 8 cardinal directions within the direction range of 22.5 on either side of the considered cardinal direction. The values of MH are determined as as follows. For H over 2 LU less than 0.05, you can take MH as 1. For H over 2 LU between 0.5 and 0.05 and 0.45, this is the value of MH. For H over TLU more than 0.45, these are the values of MH, where H is the height of the hill or ridge or escarpment. LU is the horizontal distance from the upwind as defined on the drawing. X is the horizontal distance upwind or downwind of the structure. LU and L1 and L2 are the length scale to determine the vertical variation of MH. Z is the reference height of the structure above the average local ground level. So Z here is the height of the building above the hill level. Okay, this factor might be like a little bit complicated to find, so in our calculation we may take it as 1 for simplicity. If there is no enough data, or if it is not above a hill or something, so this can be taken as 1. Okay, so this is the hill multiplier. So after all of that, so now we find V site beta equal to VR. We got VR times MC, the climate factor, times MD, and times the site exposure wind factors, MZ cat times MS shielding multiplier times MT topographic multiplier. So after we got all this factor, so now we got the site wind speed, and from the site wind speed we got the design wind speed. Okay, so after we got the design wind speed, what is the next step? The next step is to find the aerodynamic shape factor C shape. So if we refer back to the wind pressure formula here, so to find the pressure, we already know rho air, and now we got V design, so we still need to find C shape and C dynamic. C dynamic, already we can assume it as 1 because it is not a dynamic structure. If it is a dynamic structure or exposed to dynamic loads, you can determine that using section 6. But the main parameter needed, or we need to determine now, is the C shape factor. Okay, so the C shape factor can be determined using section 5 of the Australian standard. And generally, the values of the aerodynamic C shape factor C shape are used to determine the pressure applied on each surface. So to find again B equal to 0.5 rho air V design theta square times C shape times C dynamic. So C shape will determine the design wind pressure, and as you know, we have two cases for a surface. We might have, what is the difference between the direction of these two cases? We might have pressure on the surface or suction on the surface. So what is responsible for that is C shape. So the sign of C shape indicates the direction of the pressure on surface or element as in figure 5.1. The positive sign indicates pressure acting towards the surface. The negative sign indicates pressure away of the surface or suction. The wind action effects used for design is the sum of the values for different pressure effects, such as the combination of internal and external pressure on enclosed building. So some cases, or most of the cases, we have, like for example, suction on the external surface, and for example, suction on the internal surface. So the resultant will be, or the final force will be the resultant of these two. Okay, so the factor C shape, or the sign convention of C shape, is given in figure 5.2b in the Australian standard for wind. And the main thing we need to know is for the external pressures, the positive sign indicates pressure and the negative sign indicates suction. Do you have any question, guys?
No, all good. Thank you.
No worries. Sorry, I think we have missed some recording of this one. Anyway, I will go through this one again for the recording. So again, the factor C shape for internal pressure for the internal and external pressure can be found using these two formulas. C shape equal to CBI, KCI, KV, and C shape for external will be CBE and times KA times KCE times KL times KB. The main parameter in these two equations are CB. CB is the external pressure coefficient and the internal pressure coefficient. So these two parameters are mainly giving us the C-shape internal and C-shape external. Okay, the internal pressure for enclosed rectangular building for internal pressure can be found using this two table, and mainly we are looking at this table. So if the opening for walls without opening greater than 0.5. So this means that the opening in this case less than 0.5% of the wall area and impermeable area. So we have some cases for if we have one wall permeable and the other wall impermeable, like these two cases, we might have the wind wall is permeable. As you can see, this wall has some vents or permeable. So in this case, CBI will be equal to CBE, the external pressure or the external pressure coefficient. If the wind wall is impermeable, so another wall like side walls or leeward wall will be permeable, you can take CBI as negative 0.3. Negative 0.3 again means suction. Another case is 2 or 3 walls are permeable. So if the windward wall is permeable, so you take CBI as negative 0.1 or positive 0.2. So this means that we might have two cases. One case suction, One case is pressure. The other case, if the windward wall is impermeable, you take C shape again, or CBI, sorry, as negative 0.3. So in most of the cases, CBI is equal to negative 0.3. If all the wall are permeable, so take CBI as negative 0.3 or 0, whichever is more severe for the combined action. The other case, if all the walls are impermeable or there is no opening, so the factor CBI is a little bit reduced and can be taken as negative 0.2 or 0. Okay. Here the other table, table 5.1b is for internal pressure with opening greater than 0.5%. So if we have large opening or large vents, so you have to follow table 5.1. Only the first option or the first case, if it is 0.5% or less, so this means it is something close to table 5.1a, sorry, yeah, which is the previous table. So the factor can be taken as negative 0.3 and 0. Okay, so now the next parameter after CBI is the open area to volume factor, KV. KV again is a factor for internal pressure. We can have like 3 cases of KV based on this factor. So when the largest opening in the building is on a wall and the open area is greater than the sum of the total open area on the roof and other wall surfaces by a factor of 6 or more, KV is taken as follows. So if we have opening in a building in wall and the open area is greater than, like if we have opening here and the open area is greater than the sum of the total open area on the roof and the other wall surface by a factor of 6. So if the open area, the total open area on the roof plus the wall, other walls surface over the open area of this wall, which is this one here. This percent is 6 or more, so you can take K value as the following. If less than 6, if this percent less than 6, you can take KV as 1. So in our case, we can take KV as 1, but if the open area in the roofs and other walls over the open area of the designed wall is more than 6 or 6, so you can take one of these factors. So we need to find a value is called A over to the power 3 over 2 over the whole volume. So you have to find this value. So if this value times 100, which is this value, between 0.09 and 3, take this value of KV. If less than 0.9, take this value of KV. If more than 3, take this value of KV. So KV can be 0.85 or 1.085 or 1.01 plus 0.15 log 10, 100 A to the power 3 over 2 divided by the volume, where A is the open area on the designed wall, volume is the internal volume of the enclosed building. Okay, so this is generally the value of KV, which can be taken as 1 if the value of this percentage is less than 6, which is the open area, total open areas over the open area of the designed wall. Okay, so now if we return back to C-shape internal, for C-shape internal, we know CBI from table, KV from the last discussed parameter, or can be taken as 1, and then we need to know KCI. KCI and KCE are related, so we'll leave them to discuss them together. So if we know CBI and KV and KCI, we can find C shape. Okay, but I will leave KC because it is a combination between external and internal to be later after the external. So now the next is the external pressure for enclosed building, which is C shape external. C shape external again depends on the external pressure coefficient CBE. The CBE is, first of all, here we have a parameter is called H. Again, what is H? H is average height. So for example, if we have here, so this should be H. Okay, so this is H. So the external pressure, if we look here, the external pressure CBE is the surface for the surface of rectangular enclosed building given as this table we will see now for walls, and this table 5.3 ABC for roofs, and for some special roofs in Appendix A. The parameters referred in these tables are set in figure 5.2. For leeward walls, side walls, and roofs, wind speed shall be taken as the values at Z equal to H. The reference height of the building shall be taken as the average height of the roof. So the average height of the roof is, again, this is average height of the roof. So Z equal to H, where H is the average height of roof. Okay, so for example, if the highest point is H1 and the lowest point is H2, so H equal to H1 plus H2 over 2. Okay, so these are the height definition, but we need to know another parameters for enclosed building. So we have some parameters or some definition we need to know. So first of all, the definition of the walls, names, and roof slopes. So if the wind coming in this direction, so this arrow indicates the wind direction. So the face facing the wind is called windward face, or W. The opposite face on the other side is called L, leeward. Leeward face, or L. The two sides are S, or side wall S. For the roof, we will have two slopes. We have U, upwind, U, and downwind D. Okay. The other case, if we have the wind coming from this direction. So again, the wall facing the wind is called windward. So the other side will be leeward, L. And the two walls here are side walls. But here, the slope of the roof is not facing the wind. So here we call the roof R or cross wind. So R is the cross wind if the wind coming parallel to the slope. Do you have any problem with the definition by the standard, given by the standard? So we have some 4 definition for the walls and 3 definition for the roof. So here 3 definition for walls and and 3 also, and 3 definition for the roof. Okay, this example here, if you see here, if the wind coming in this direction, so we have windward and the other side leeward and 2 sides, and the roof we have upwind facing the wind, downwind the other side, and this 2 are parallel to the wind, so we have cross wind. Okay, these are the given definitions because the parameters of CBI is given based on this definition. So the first step is the walls external pressure on coefficient CBE for rectangular enclosed building windward. So table 5.2 is for windward walls. So 5.2a for windward walls. So H, if the height of the building more than 25 meter, the parameter CBE is 0.8. And if the height less than 25 meter for building on ground, 0.8 and 0.7. 0.8 when speed varies with height, or 0.7 when wind speed is taken for Z equal to H. For elevated building, 0.8. So what does this mean? This means, let's write it here. So if we have this building, for example, and this is in 3D. So if the wind coming from this direction, so this wall is leeward, and this wall is windward. So I just need to delete this one. Okay, so if we have this building, so we have the wind in this direction. So this wall is the windward wall, and this wall is the leeward wall. So in 3D, this is our building in 3D. So the parameter or the coefficient PBE will be equal to 0.7. Positive 0.7 means pressure. That's why I put the arrows like that. So it is acting into the wall. So the vector is 0.7 if the building height is less than 25 meters, for example, and we have wind speed V design theta at Z equal to H. So this parameter is 0.7. So if the wall, this is the wind coming in this direction. So this windward face, the parameter CBE equal to positive 0.7. Okay, so this is the interpretation of this table here. So if, for example, we have case like this, so the parameter is given as positive, this means that pressure on the windward wall. Another table for the leeward wall, external pressure for leeward wall. For the leeward wall, depending on the direction, 0 or 90, and the roof shape, hip or gable. You know the hip and gable roof. So this roof, if it has one slope like this, so this is hip roof. If it has two like this, so this is gable roof. So hip roof means one slope, gable roof means two slopes. And based on the roof pitch alpha, so the roof pitch is the angle of the roof. So if the angle less than 10 degree or more than 25 degree, or so based on alpha, the slope of the roof, and the ratio D over B. So what is the ratio D over B? So for example, if we have the wind from this direction here, we have B and D. So B is the width of the building facing the wind, and the D is the perpendicular dimension. Okay, if we look here, so this is given here. So if this is the wind direction, B is this one, the width facing the wind, or the width of the wall facing, or the building facing the wind, and the D is the perpendicular dimension. If you see here, when the wind in this direction, the other direction, what happened to B? B, this is B. So again, the width of the building facing the wind, and D is the perpendicular. So based on D over B, if it's less than 1, 2, or 4, so you can take the external wind pressure. For example, if we have gable roof and most of the building alpha or the angle is less than 10, so the wind direction 0. So if D over B less than 1, so CBE is negative 0.5. So if CBE is negative 0.5, what is the negative means in this case? CBE negative 0.5. This negative means suction or tension or pressure. Suction. Okay.
Can I just ask a quick question, Ahmed? Just with
Yes,
the
good.
angle,
Yep.
yeah, the roof pitch. Would you use that to find the height for that previous formula that you had there for your two?
Here?
Because like if you're given a height of a frame, say 10 meters, to work out the height that you use in that previous formula, would you use that to find your actual height, or?
Yes, depend on, like, for example, depend on what is given. Like, for example, if
Okay.
for example, here, if we have this frame, for example, so if the height given, this is the height given, for example, 10 meter, and this, for example, like 20 meter, and this alpha equal to 5 degree, for example. So you will need to use the alpha to find this height. For example, H1 or something. So using the trigonometry calculation.
Yep.
So we have alpha equal to 5 degree, and here is, like, for example, let's say
What?
like
20.
any x, 10 meter.
10 meters. Yeah.
Yeah. So x equal to 10 meter. So this value is H1. So how we can find H1? H1 will be, it is the opposite to the angle, right? So you have the adjacent
sine.
and opposite. No, sine will not be if,
sorry.
yeah, 10.
10.
Yeah.
Of
So
5 degrees.
it will be 10, 5 times x, which is 10 meters. So you can find H1. So the total height or the highest point of the building will be H plus H1. So now you know the highest point and the lowest point, so you can take or get the average H, right?
Yep.
Yeah, let's name this as H2. So you have the average H by will be, for example, if we get this, like, just calculate it to be exact.
Yeah. So you're not finding the midpoint of the roof there. You're finding the average. So
Because the highest point will not be like this is what is the standard need to, because maybe the highest point will be more
it's
like not the actual height, or not all the building has this height, so like try to balance between the lowest point and the highest point. But this how to, you need, if the height of the lowest point is given, so you need to use the angle to find the highest point.
Okay, thanks.
No worries. So if we return back to here, the idea is just is depending on the percentage D over B and the roof pitch, so you can find the factor CBE. So CBE negative means suction. So if you can see here, all of them are suction. So any leeward pressure will be suction. And here, any windward pressure will be pressure. So the windward wall all the time under pressure, the leeward all the time under suction. What is the third type of wall we have in our building? Here, for example, so we have side wall and side wall. Okay, so the side wall has different table 5.2c. So the external pressure, CBE, enclosed building is side wall, need to be found using this table. Again, all the factors are negative, so means suction. Okay, but here the horizontal distance from the windward edge, so the value of this factor is not uniform. So here for all the cases, we have only one value, but if you can see here, we have different value depend on the distance. So what this mean? This means that just maybe create a new one. So if you look at the table, we already have this our building. So when the wind coming from here, which walls are the side walls? These two, right? So this is and this is, and this is the blue one is windward, and the green one is leeward. So it is given from the table that from 0 to 1h, the factor CBE is negative 0.65. From 1h to 2h, negative 0.5. From 2h to 3h, negative 0.3. From 3h up to the end of the building is negative 0.2. What this mean? This means that the factor and this distance is from the windward face. So we are calculating the distance from this face here. So this is our windward face. So this means that the factor is not constant and it is something like that, steps like this. And the main idea is all the factors are negative, so it is under section. So the first value is from 0 to 1h. What is h? H is the building height. For example, if this width is 30 meter, okay? Building height h is 10 meter. So the first 10 meter from 0 to 10 meter, how much is the factor? Negative 0.65, okay? So this one. From 1h to 2h, how much 1h to 2h? The next 10 meter, so from 10 meter to 20 meter. The factor is negative 0.5. The third is from 2h to 3h, negative 0.3. So from 20 meter to 30 meter, so it is negative 0.3. If the building height or the building width, for example, 40 or 50, so the remainder will be negative 0.2. Okay, so if we put this here again, so this is section, this negative 0.3, negative 0.5, negative 0.65. Okay, so what is the difference between side walls and leeward wall and windward wall? The pressure on the side walls is steps, but the pressure on the other, like leeward and windward, is uniform. So if I want to add all of them at once here, what you expect? It is one value or steps for the windward? It is one value. The CBE, sorry, was 0.7, right? For the leeward wall, what was the value? It was suction or pressure? Suction. And the value was, for example, negative 0.5. So this is the CBE values on the walls if the wind coming from, what is the wind direction here? West. If the wind coming from west. Do you have any problem with that?
No, I think that's all good. That's all obviously all for the external pressures.
Yeah, the external pressure, because the main parameter, as I told you, is the CBE. So if you know the CBE, so the C shape will be same. So the shape of the pressure is based on the coefficient CBE. Oops, sorry.
Yep.
So again, the C shape factor is based on CBE. Okay, so this is the CBE, or the external pressure coefficient for the three types of wall. As you can see here, we have table for side wall, table for leeward wall, and table for the table for the windward wall. Okay, I just not uniform.
I'm not seeing your diagram. I'm not sure if
Oh.
everyone else is.
Okay, sorry. Can you see it now?
Yeah, that's got it. Thanks.
Sorry, when the file closed, I didn't share the screen again. Sorry. Okay, so the idea of, again, just to remind you, for the side wall, the wind or the factor CBE is non-uniform. It will be steps. But for the others, for leeward, it will be uniform because it is only one value. And also for the windward, it will be uniform because we have only one value. Okay, because this is very important. Okay, so now this for the walls, and how about the roofs? The roofs will be found using table 5.3a and b and c. Table 5.3a for roof, external pressure, CBE for rectangular enclosed building, for upwind and downwind and crosswind, roofs less than 10. The slope is less than 10. And table 5.3b for external pressure, CBE for rectangular enclosed building, upwind for more than 10. And usually our building will be less than 10, so we might not need to use this one. The third one for roofs, external pressure, CBE for rectangular enclosed building, downwind slope, and crosswind slope for hips roof more than 10. So might not need to use this two now, but this, if you have any other case for the slope more than 10, you can take this, the value of this from this two. So again, if we look at the table here, we have crosswind slope for gables, downwind slope for monoslope for all alphas, or upwind slope and downwind slope for alpha less than 10. The horizontal distance from the wind roof from 0 to 0.5 h. So again, the values are non-uniform. So for the roof, it will be also non-uniform and depend on HD, if H over D less than 0.5 or HD of more than 1. What is H and what is D? So again, if we add a new page. So here we are dealing with roof. So if this our building and the wind coming from here, So this, the green one here is upwind or U, and here we have the yellow one is downwind or D. So the standard give us, and again, alpha is less than 10. So in this direction, if the wind coming from west, we will have upwind and downwind. The standard give us the values as follows. So from 0 to 0.5 H, from 0.5 H to 1 H, 1 H to 2 H, 2 H to 3 H, and more than 3 H. The factors are depending on H over D. Might be 0.5 or 1. So if it is less than 0.5 or more than 1. What is H? If you remember, H was the average height. What is D? So if we go up again, this was D. What is D? If the wind direction coming from this direction, so D is the dimension perpendicular to the width of the building or the parallel to the wind direction. So for example, here, if the wind coming from here, so this will be D. This is B, and this is D. And this is upwind, and this is downwind. Okay, so depending on the value H over D, you can find the value. For example, if the value H over D less than 0.5, so we have the parameter 0.9 and negative 0.4 and negative 0.9, then negative 0.9, negative 0.4, negative 0.5 and 0, and negative 0.3, 1.1, negative 0.2, and positive 0.2. What does this mean? This means that we have two cases should be studied in this case. So we have this parameter together and those parameters together. So for this case, we will have two cases. The first case, I will put it on this diagram. So again, we are starting our dimensioning from the windward wall. So from 0 to 0.5 H, so for example, this is 0.5 H. So 0 to 0.5 H, the value is negative 0.9. So negative means suction, so this will be the factor, negative 0.9. From 0.5 H to 1 H, it is again negative 0.9. So this actually means from 0 to 1 H, it is same value for our case, but for other cases may be different. That's why they put it in the table like that. From 1H to 2H, for example, up to here. So the value is negative 0.5. From 2H to 3H, negative 0.3. So let's say for this example, our width of the building was like 30 meters again, and our building is 10 meters. So we have only from 0 to 3H. So 0 to 30 meters, which is 3H. If we have more than 3H, you can take it as negative 0.2. So again, for the roof, non-uniform pressure or non-uniform C shape. Okay, so this is our first case. What will be our second case? The second case will be the other set of values. So this will be our second case, case number 2. Again, the wind coming from here. This is our windward wall. So this is our dimensioning. We have from 0 to 1h, same value, which is negative 0.4. So we have negative 0.4. The other case is from 1h to 2h. We have negative, 0. So in this case, we have 0. So there is no pressure in this case, 0. And then from 2h to 3h, we have positive 0.1. So what is meaning of positive 0.1? Pressure. So in this case, we will have 0 values in the middle and suction at part of it and pressure on the other part. So here again, as a reminder, we have this is the upwind part, and this is downwind part of the roof. Okay, so for the roof, we have two cases. Case number 1 and case number 2. Case number 1 was the first set of parameter. Case number 2 was the second case set of parameter. Okay, guys, do you have any problem, guys?
Why do they have two cases for that?
Why do you have two cases? Because this is they have two critical cases. If you see the parameters here given by the standard, so two cases might happen for this wind direction, or sorry, for this roof direction. So we might have this set of values, or we might have this set of values. Case 1, case 2.
Okay, so say for our assignment where it asks us for the external pressures, we have to give both cases. It doesn't relate to the site or anything like that.
Yeah, for any design of wind, so you have to consider both cases, because the problem in the wind, it has a lot of possibilities. That's why it's a little bit long and complicated.
Yeah. Okay.
So for example, if you see any tables that have two values, for example, this table 5.3, it has only one value. So this one case. But for example, this table, so you have two values. This means that you have two cases. So for the roof, in this case, the standard give us two values. These two sets, if you see here, what is the difference between case 1 and case 2? Case 1 has almost all suction, and a higher value of suction, like negative 0.9. For case 2, what we have lower value of suction, and part of the roof has pressure value. Okay, so the difference here is case 2 has a pressure value on the roof, but case 1 has suction value. And also because we are not designing for wind alone. So what else we have to consider in our design? What is other loads we have? Like we have dead load and live load and wind load, right?
Yep.
So not only wind load. So for example, if you are designing this roof, so you will have like load downward from dead load and load downward from what else? Live load. And you have upward wind, sorry, upwind pressure, upward pressure from wind load. So when you like sum this together, so the resultant might be downward or upward, right?
Yep.
So you have some loads are downward, some loads upward. So this might be upward or downward based on the values. So the standard try to give all the possibilities and all the like to assume the critical case. That's why I give us this case here, because this case has the wind downward. So if you have wind downward here plus dead load downward, sorry.
Oh, yep, yep.
Plus,
So you're
yeah.
going to get more pressure
Yeah.
on some of the
So this, yeah, somewhere
members.
this
Yep.
area will have more critical loading because it has wind pressure from the wind. That's why some cases might give us upward critical load here, and this one might give us the critical downward load.
Yep.
So just
Okay.
to give all the possible cases to give us the most critical ones.
Yep. Thank you.
No worries. I know it is a little bit like complicated and a lot of details, but the wind design has a lot of possibilities. That's why it is that complicated in the standard. So if you have any other question, just let me know, guys. Thank you. Okay, so this is the factors CBE for the roof and the walls. Do you have any question for the wind factor or the CBE factor for the wind and roof? For the wall, sorry, and roof. So after we get this factor, so we need to know so we have C shape external equal to CBE times K. Just quickly. Times KA times KCE times KL times KB. So now we know CBE. We need to know the other parameter. So KA is the area reduction factor. The area reduction factor, just quickly see here. The area reduction factor, Ka for roofs and walls. For roofs and walls of enclosed building is taken from this table 5.4. So table 5.4 here is the area reduction factor. If the tributary area A less than 10 meter, can take Ka for roof and sidewall as 1, and for windward walls for each less than 25 meter, you can take it as 1. Also for leeward wall, you can take it as 1. For tributary area 25 meter, taken 0.9, 0.95, and 1. For tributary area more than 100, so you can take Ka as 0.8, 0.9, 0.95. For our calculation, we can take Ka as 1. Okay, so our focus will be on our calculation. You can focus only on the C shape parameter when you calculate C shape parameter, depend only on CBE and CBI. So this is the main parameter to consider. Another factor is the KC. We have KC for internal and KC for external. So KCE for external, KCI for internal. KC is a factor to combine the external pressure factor and internal pressure factor. So this can be found using table 5.5. So we have, for example, 3 effective phases, pressure from windward in combination with wind roof. So as you can see here, we can consider this case only if you have 0 internal pressure. In our case, we will consider this one. So we have internal pressure. So this will be our considered case, because this, as you can see, you have external pressure and also internal pressure. So in our case, we can take KCE and KCI as 0.8. So KCE and KCI for our calculation will be 0.8, as we considered we have internal pressure and external pressure. Okay, this table, the remainder of the table for other cases, if you need it, you can have a look, but we will not need in our calculation. And another parameter we have is the local pressure factor, KL, for cladding. Also in our calculation, we will take KL as 1. But generally, KL is the local pressure factor, can be taken as 1 in all cases except when determining the wind action applied to cladding. So if you are designing cladding or their fixations or fixing, you need to consider the value of KL. Okay, so I will not waste the local pressure factor in our calculation. But anyway, so this might be needed only if we design the cladding, or like, for example, this also might be needed if you are designing the fixing for solar panels, for example, on roofs. So this might be needed. Okay, so for any like fixing or on the cladding or the roof sheeting, you can consider KL. Okay, also the final parameter we have is the permeable cladding reduction factor, KB, for roof and side walls. Also, KB can be taken as 1 in our calculation. So the permeable cladding reduction factor, KB, shall be taken as 1 except where an external surface consists of permeable cladding and the open area ratio is greater than 0.1% and less than 1. The values are given in table 5.8. So 5.8 for permeable cladding reduction factor, KB. So for our calculation, finally, we have C-shape external equal to CBE, this given in the tables for walls and roofs, times KA taken as 1, KCE. How much KCE? We mentioned KCE will be 0.8 times KL1 times KB1. So again, just emphasize that the main value we need to consider is the value of CBE, the external pressure coefficient. And finally, to find the final pressure or the wind pressure, the dynamic response factor C dynamic shall be taken as 1 as well. So C dynamic in our calculation will be 1. C dynamic can be or shall be considered if the building and freestanding towers whose natural frequency is greater than 1 hertz. Poles and chimneys with height to average diameter less than 5. Ground-mounted solar panel with frequencies greater than 5 hertz. Okay, so this is generally what we need in this calculation for wind. Do you have any question, guys, regarding the wind calculation?
No, all good.
So let's quickly have a look on the tutorial. Thank you, Paris. Okay, guys, can you see the screen now?
Yep.
Okay. So this is an example of calculating the site wind speed. So we need to calculate site wind speed V site beta in the north direction for the following site, assuming ms equal to mt equal to 1. So if we have a 15-meter high portal frame with an importance level of 2 in an open terrain site, like terrain category 2, so we have importance level 2 and TC2 in Adelaide, SA, with B equal to 48 meter and D 30 meter. Rafters are at 6 meter centers, span 15 meter. The purlin and girts are spaced at 1200 centers. So if we look at this one, 10-meter high portal frame in an exposed site in Adelaide. So if we look at the map, so Adelaide is in wind region A5 with non-cyclonic building or region. So the region is A5. The important level is 2. Just so the annual probability of exceedance is 1 to 500 from this table in NCC volume 1 or from AS 1170.0. So there is another standard that also gives us the importance factor, which is the national code volume 1. So you can find this one or the other one I have used. So for importance level 2, let's open the other one as well to compare. Can you see the Sterling standard?
Yep.
Yes. So both are given same values, but anyway. So here, if we have the occurrence, the importance level 2 with non-cyclonic building and assuming the design life of 50 years. So how much is the occurrence interval? 1 to 500. Also from the national code. So we have importance level 2. So annual probability of exceedance for non-cyclonic wind is 1 to 500. So are not earthquakes, and this not cyclonic, so 1 to 500. So we are looking at V 500, right? So if we go to the table, V 500 is equal to 45 meter per second. Okay. So I just open the module again. As you can see, you need the standard. So, but anyway, so I'll still see my screen, right? So now, what is V in this case? 500. What is the region? A5. So how much is the speed? 45. So here from the table, 45 meter per second is the speed. What is mzcat? So if we go to the standard here, so here mzcat, how much is the building height? 10 meter. What is the terrain category? 2. Let's have a look. So oh, sorry, the height is 15. Okay. Can you adjust this one, please? I will adjust it and the height is 15, not 10. Okay. So if we look here, how much is the height? 15 meter. So terrain category 2. So how much is the parameter mzcat? 1.05. Okay. So mzcat for this case is 1.05. So v side beta for the north direction equal to VR 45. MC, the climate parameter is 1. How much MD? If we go to the module again, so we are looking for the north direction. So we are north and terrain category, region A5. So how much MD? MD is 0.95. So here MD is 0.95 and mzcat is 105 and 1 is ms, 1 is mt. So the final result will be 44.89. And here is MC and MD from the tables. Okay, do you have any problem with this one? It's just a simple one. So the second one is a 20-meter height building. 20-meter height building in an a flat roofed building, importance level 3 in a very exposed site at Port Hedland, WA. So for case 2, or sorry, question 2, the wind region is D, extreme cyclonic area. So if we look at the map, we need to refer to the map to find the, where is Port Hedland. So if you see here is Port Hedland. It is region D, and region D is a severe cyclonic area. So the wind region is extreme cyclonic, importance level 3. So the annual probability is 1 to 1,000. So if we look from the national code, it is 1 to 1,000. If we look at the standard here, the 1170.0, so we have importance level 3. So the occurrence level is 1 to 1000. Okay, so it's same values. Or from top here, we have importance level. For cyclonic, it is 1 to 1000. So we are looking at VR equal to V1000. So if we go to the regional table, so V1000 and cyclonic, so how much is the force? Sorry, the speed. So V1000 cyclonic D is 85 meter per second. So V1000 is 85 meter per second. Here it is very exposed area and no obstruction was mentioned, so it terrain category 1. So MZCat for terrain category 1, 1.14. So V site beta equal to VR 85 times MC1 times MD 105 because north direction times 0.9. Sorry. Just if we just here MC is 1.05. If we go to the table to check. So here is the table of MC. So we are cyclonic region D. So how much MC? 105. Also for in direction region D. So MD is 0.9. And also let's see MZCat. MZ category building 20 meter high and terrain category 1, so it is 114. So all the parameter here is correct. So 114 for terrain category 1 and MC 105, MD 0.9 times 104, 1.14. MS was taken as 1 and MT is given as 1. So the V side beta for the north direction is 91.57 meter per second. Okay. Is that okay?
Yep.
Yep. Okay, do you want to try them and let me know if you have any question, or do you want me to explain further? I have explained most of the requirement in the lecture, but if you have any questions, just let me know. Is that okay?
Yep, all
Okay,
good, thank you.
All good. And have you started working on the first assignment? Yes, all good.
Yes, started, yep.
Okay. And you mentioned you have a question, William? Can you
Yeah, I
have a
just
discussion?
I just had a question just relating to last week's work.
Yes, sure.
When calculating, I think it was the load for the in the assignment, trying to calculate the load on the roof girder. Do we, when we're calculating the uniformly distributed load, for a girder, do we include the self-weight of the girder? Because I think in the example, I couldn't see the self-weight being included in the formula from last week. Not sure if that's very clear or not.
Yep. Can I use my screen? Can you see the screen now?
Yep.
Yeah. So, for example,
Because
if
we
we
got
have,
we got the roof sheet and the purlin, which
Yep.
the roof girder supports. So when we calculate the weight that the girder is supporting, do we include the self weight of the girder with that as well?
Yep. So just see, like, say this is an example of similar to what you have in the assignment, right?
Yeah. Yeah.
So if we have column here, so this is an internal beam. So the main thing here is, as we mentioned last week, so we have the load width of the rafter is half of the distance from left, half of the distance from right, which is the spacing. So the load width of each rafter is one spacing, which is 6 meters.
Yep.
So the load width of the rafter is equal to 6 meters. What are the loads on rafter, or where the loads from rafter come from? The loads on rafter come from,
You have the purlins and the
yes,
sheet.
roof sheeting, and some items related to the roof sheeting, like insulation and ceiling, for example,
Yep.
is for the roof, right? And
Yep.
what is carrying the roof sheeting? Purlins,
The purlins. Yep.
yes. And then the beam carry itself, so on or self weight.
Yep. Okay.
Okay, so the roof sheeting will be the weight of the roof sheeting per square meter times what? Times the load width. So the roof sheeting need to be multiplied by the load width. Also the insulation and ceiling, because they are in terms of kilonewton per square meter, So we need to multiply by the load width, because what we need to find, the load on the rafter as UDL,
Yeah.
right?
UDL. Yep.
So let's say the dead load on the rafter will be like roof sheeting plus insulation plus ceiling plus purlins weight plus self weight. All should be finally in kilonewton per meter. This is the final unit to find the load as UDL. So the purlins will be found based on the given spacing, right? The spacing of the purlin is given.
Yep.
So for example, it is 1.5, I think, meter, if I
Yep.
remember. So what you need to do is find, like, for example, one of them, the weight of one of them, and then multiply by the number, okay, divided by the length of the rafter. So weight of one purlin. So you are saying something?
Oh yeah, I was just going to say, last week when we did the example, it seemed to just use a formula, like it was the weight of the purlin was just 1.8 over the area plus 0.12. So I didn't really consider the weight of the insulation or the ceiling or the type of sheeting or anything.
No, but this was the life load. This was the formula for life load, but this is the dead load. I'm talking about
okay. Yeah.
dead load. Right?
That's what I'm misunderstanding that. Yeah.
Yeah. The life load is the formula you mentioned, 1.8 over 8 plus 0.18.
Yeah.
Well, sorry, plus 0.12.
Okay. That's where I was getting confused. Yeah.
Okay. So sorry for the weight of the purlin. So one purlins times the number of purlins divided by the length of the beam. Mm. And here also, sorry, just need to times. So for example, because here, as you can see, what is the difference between the purlins and the rafter? Are they in same direction or?
No, yeah, they're
Yeah.
running opposite
So,
directions.
yeah, opposite directions, they are perpendicular. So what we need to do is just concentrate the load from the purlins to be like a point load on the rafter, and then
Point
we,
load. Yeah.
yeah, redistribute them again on the lens. So what we will find, one weight of one beam is this is the first one. So times the number of beams, so we find all of them, times the load width, or 6 meter, times 6 meter, or in bracket the load width, or let's write it as length of rafter. Sorry, length of purlin. Okay. So we will just refine this one here. So the weight of purlins equal to weight of purlins, weight of one purlin, times the length of purlin, times number of purlins. So this will be the total weight of the purlin divided by, to make it distributed, we divide by the length of rafter. Is that okay?
Yep, I think so.
Yeah. Yeah, the last one you mentioned is the self weight. The self weight
Yep.
is based on the section. So for example, if we are using, let's say 310 UB
32.
50, yeah, 32, whatever the value
So
is.
is that 32 kilograms per
Yeah.
meter?
So 32 kilogram per meter. So the self weight is, the mass is 32 kilogram per meter. So this is a mass. So you need to convert to a weight. So
kilonewtons.
yeah, kilonewton. So 32 times 10 divided over 1,000. So it becomes 0.32 kilonewton per meter. So there is no need to do, just assume a section, and the section already has, or if it is given, so you use what is given.
Yeah.
But the idea is the weight of the section is in kilogram per meter. So we need all of them, so they can be summed up. All of them need to be kilonewton per meter. So if you calculate them all, so you will find it kilonewton per meter.
And the weight of all the other materials, is that in the
Yeah, all other
standards?
material in the standard
1170.
1170.0, 1170.1.
Okay.
0.1 for the material, the permanent load or dead load and life load. This one for the load combination, and 0.2 for the wind.
Okay. There's lots to do. It's
There's not
a big,
this long one.
yeah. I mean, it's probably not long, but it's just a bit time consuming because looking everything up. But that's at least made that much clearer. So thank you.
No worries. If you need example, maybe I can send you like solved example, but I don't know why you confused because of the example between the dead load or life load, or just.
Oh no, I think
yeah.
last week I just misunderstood the material a little bit with live load and dead load. That was all. That was just, yeah, I probably wasn't concentrating at the time. Yeah. So,
I noticed 3 hours is too long time to concentrate, but
yeah,
anyway.
especially after a full day at work, I'm pretty toasted by 8 o'clock. So
sorry, but this what we have put for the timetable for the subject.
Yeah, no, that's okay. No, that's fine. At least I can attend it when it's after work. Otherwise, I just can only watch the recording. So
yeah, at least to have some like
some time for questions. So
yeah,
it's good.
some discussion. Yeah, that's a good thing. Anyway, if you have any problem, guys, just send me the question by email, and maybe I provide more material or solve the example, or maybe something like what we have done here. Okay, but do you have any other question?
All good. Thank you, Ahmed.
No worries. I just maybe share this discussion with you. This if you want. So just a second, I will send it by in the chat.
Thank you, Ahmad.
Thank you, Bars. Thank you. I just send you. I will save this image and send it to you now. Just maybe a few seconds. Sorry, guys, trying to find it. Seems like no option to send it here. Okay, but I will share. I will add them to the website. Sorry, guys, I will send it by email because there is no option to share something from computer. So I will send it by email.
No
But
worries.
have you watched the videos from previous weeks? I already added them to the website. Are you able to access them or not yet?
Yeah, I watched a little bit of the one from last week's recording, and there was one also from last year, I think.
Yes, because it should be there was some recordings to have a look on them before the workshop so that we save some time.
Okay. Yeah.
But all the links was damaged, so that's why.
Yeah,
I
they
might
seem
need yeah.
to work. Yep, no problem.
Yeah, I already updated them, but anyway, I will update the next few weeks. So if you can have a look on them before coming to the lecture, so that we can save some time on discussing the equation and so on, and go directly to the examples and so on.
Okay, sounds good.
Yeah, no worries. So I will upload the recordings of today, update the recordings from like the pre-recorded ones for the next few weeks as well.
No worries. Thanks,
Okay.
Ahmed.
Thank you, guys, and have a good night. And see you next week.
Thank
Thank you,
you. Have a good
guys.
night.
Bye.
Thanks, Bart. Thanks, Nicholas. Thanks, William. Thanks, Paris. See you all. Thank you.